So I want to look at the proof assigned in section 1.5. It's number 33. It says prove that if B is obtained from A by performing a sequence of elementary row operations, and there's a second sequence of elementary row operations which when applied to B recovers A. So let's see what we mean by this. First of all, before we proceed, I want to share two important theorems in this section. 1.5.1, which we're going to use. I'm going to use elementary matrices basically to do row operations. So first of all, remember this: if elementary matrices, remember, are obtained from the identity matrix by performing one row operation. All right, so if I interchange two rows of the identity matrix, I get an elementary matrix. Here are some examples of elementary matrices, right? Interchanging two rows of the identity matrix, multiplying a row of the identity matrix by a constant, or adding a multiple of one row to another in the identity matrix. So those are all elementary matrices. Now here's the important thing. If an elementary matrix E results from performing a certain row operation on the identity matrix, and if A is an m by n matrix, of course we're talking about elementary matrices, notice this is the identity matrix of size m by m, right, of order m. So the elementary matrices will be m by m. So if A is an m by n matrix, then the product EA, which would be defined, right, E is m by m, so the m's match. This resulting matrix is what? It results when this same row operation is performed to A. In other words, it performs that elementary row operation. You know, for example, here, this elementary matrix was obtained from the identity by what? Adding 3 times row 1 to row 3. And so this is how we obtain this from the identity matrix. If I multiply this matrix times this matrix A, is 3 by 3 times 3 by 4, I get this. And notice the net effect is to add 3 times row 1 to row 3, right? 3 times 1 is 3, added to 1 gives me 4 down there in the last row. Of course, 3 times 0 is 0, so the 4 remains this unchanged. 3 times 2 is 6, 6 plus 4 is 10, 3 times 3 is 9, 9 plus 0 is 9. So that's the effect. So that's important, you have to know that. And then the other thing we're going to use is this fact here, and that is that every elementary matrix is invertible, theorem 1.52, and the inverse is also an elementary matrix. And it's pretty clear that elementary matrices are invertible because, you know, they come from row operations, and we can just undo row operations with another row operation, which results in the corresponding inverse elementary matrix. So for example, if I interchange rows 1 and 2, to undo that, I'll just interchange rows 1 and 2 again. So the inverse of that elementary matrix is actually itself. If I want to undo multiplying a row 1 by 2, what do? I multiply row 1 by a half. That will undo the effect. And if I add 2 times row 1 to row 3, I can undo that by adding negative 2 times row 1 to row 3. So those are the ideas. So let's go back to this theorem and prove it, which says, I'm going to just write out what it says here to be able to write the proof, and that is, if B is obtained and let's let B well, let's just write out, if B is obtained from A by performing a sequence of elementary row operations I should have put this in the beginning, but let's just assume obviously A and B have to be the same size, right? If we're doing row operations to A to get to B, I'm not going to change the size, so assume A and B are size m by n. Okay, so if this is the case, then there exists a sequence of, and I'll go ahead and say size m by m elementary matrices such that I'm sorry, let me get the sequence out first. The sequence of elementary matrices, and we'll call them E1, E2, all the way to EK, such that. Okay, so I want to actually talk about these guys. So in other words, I don't know how many elementary row operations you've done. I'm gonna just say K of them, and for each elementary row operation you do, there's a corresponding elementary matrix. And so when you start with matrix A, you're going to multiply by E1 to perform the first row operation on the left, right? That it will perform that row operation. And then we'll do the second row operation by multiplying by the corresponding elementary matrix all the way until we multiply finally on the left by E sub K, and that will get me the matrix B, right? That's what it's saying. If B is obtained from A by performing a sequence of elementary row operations. So that's the power of elementary matrices. We can do it in a proof this way. And then again, we know what? That the elementary matrices are invertible, thus we can do the following. I can multiply by the inverse of this first matrix on the left. Of course, I'll do it on both sides. And notice, because the sizes are m by m for all these E matrices, and of course A and B are m by n, all these products are defined. Okay, both sides are m by n matrices after we do all the multiplying. But here, what happens? The E sub K inverse times E sub K is what? The identity matrix. And sort of this peels off the E sub K. And then we have the E sub K minus 1, right? Multiply both sides on the left by its inverse, right? And then continue to multiply on the left by the corresponding inverse over here, and peeling each one off. And finally, we'll multiply by E sub 2 inverse, and finally E sub 1 inverse. So eventually we get to what? A is E sub 1 inverse, E sub 2 inverse, dot, 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 E sub K inverse times B, right? So continuing that manner, we get to here, which says since elementary matrices are invertible and their inverses are elementary matrices, there exists a sequence of row operations, elementary row operations, that transform what? Now we're multiplying B by this elementary matrix, so doing that elementary row operation and so on, right? And we get what? A, that transform B into A. And that's what we're supposed to prove. And so you can see the actual, basically we're just undoing the row operation. So I did a sequence of row operations to A. I simply undo those row operations in order to get back to A. So I do the sequence of row operations to A to get B, do the inverse operations, right? Notice in the reverse order too, right? So to undo that to get back to A. And that's the proof.